Welcome to the final talk of Unite in this room, how Unity's serialization system works. It is about how Unity's serialization system works. I believe in truth in naming. The presentation trainers that I went to back in LA, they advised me I should always try and start every talk with some kind of hook to get everyone's attention, some kind of funny story or joke. In LA, I hid behind the podium and then leapt out, kind of pretending to be a movie announcer, because it was Hollywood. And this time I was really racking my brains trying to come up with what my hook should be. And sadly, I didn't have time to execute on the idea I thought was best, which was to get a box of cereal and kind of cross out the name and write Unity on it, and then just stand on stage holding a box of cereal saying, serialization. So if you could just imagine that I'm holding a box of cereal, then the hook basically still works. So that's great. So what am I going to talk about today? I'm going to talk about what Unity's serialization system actually is and what it's for. There's a lot of misconceptions. A lot of people think it does a lot less than it actually does. I'm going to talk about how it works on the C++ level. We are going to show some C++ code in this talk. So that will be fun. And I'm going to talk about how it works at the C# level. So when you're writing your monobehaviors, your scriptable objects, and they're getting serialized, like what's actually happening? How do these systems kind of fit together? Now, I will warn you now, this talk is kind of pure theory. Like, I'm not going to try and tell you, you should do this in your project, you should do that in your project. I'm just going to talk about what the engine actually does under the hood. I'm just going to try and tell you how it works. This is basically, I could pretty much give this talk to engineers starting at Unity as developers. I'm just going to talk about how the system works. It's up to you to kind of then decide how that knowledge relates to your project. But I think that in order to successfully debug issues, particularly with performance around serialization and so on, one of the things you need is a good understanding of how the system actually kind of is designed and how it's supposed to work. So I'm going to try and give you that understanding today, and then you can then kind of take that and try and build on that and use that to kind of reason about problems that you run into that are related to serialization. So, what is serialization? First good question. There's a lot of sort of dictionary definitions of this floating around, but this is the way I'm going to try and define it, and fingers crossed none of you will complain too much about it. The purpose of serialization is to take data that is kind of wherever, in whatever format, and to lay it out in a nice kind of linear sequence, one thing after the next. Okay? And then deserialization is the opposite of that, taking nice laid out data one after the next and then blatting it to all the places it needs to be in memory, all over the place, right? And this is possibly something that you guys don't have to think about very much as C# developers, is exactly how things are laid out in memory. But it's something that is inescapably true. The data has to go somewhere. A lot of simple structures, maybe they are already basically serialized, but a lot of things, you know, with strings or arrays or things like that, they're kind of blocks of memory all over the place, pointing at each other, kind of connected together in a funky little graph. And what we need when we're going to be writing it out to disk is to lay it out in a file, one thing after the next. So that's what we'd use serialization for. But it's not the only thing we use it for. I mean, yes, saving and loading data. And the obvious situations where we do that in Unity, of course, we have binary serialization that we use both in the editor and when building the player. We have YAML serialization or text mode serialization. We have JSON serialization. Some less obvious cases where we use serialization as well. The undo system actually functions by serializing an object, and then you change it, and then it serializes it again and diffs them. And that's how it works out kind of what you've changed. The editors also make heavy use of serialization. If you're looking at an object in the inspector, a lot of the time, we have not we're not operating on the C# object. We're actually operating on the data via the serialization system directly. And animation as well is another good case. When you're animating a transform or something like that, we've got fast paths in place. But it's possible to animate kind of any float property on any monobehavior anywhere, right? We actually do that through serialization. We serialize the object, we modify the fields that you're animating, and then we deserialize. And that's how we animate kind of any field on any object. Obviously, it's not the fastest way to animate something, which is why we introduce these special fast paths for transforms and materials and the most common things you want to animate. But as a nice kind of fallback, we can use the serialization system to feed data into any field you want on any object. We also use it for some non-reading and writing, non-serialization cases. We call it a serialization system, but it is actually quite a bit more than that to us these days. So it's a bit of an abuse. It's kind of going beyond its original constraints, but it still ends up being very nice for us. The particular things that we use the serialization system for that are not serialization in Unity includes instantiating things. We will actually serialize an object and deserialize it again to clone it. When we're unloading unused assets and we want to walk the object graph and work out kind of which assets are still needed, we use the serialization system to do that as well. And I'll get into exactly kind of what that looks like shortly. We use it when we're remapping references. So particularly when you instantiate a prefab, you're starting with a game object and a transform and other components and so on, and they all kind of refer to each other. And if we just cloned them like directly, kind of as a sort of shallow copy, we'd end up with clones that still refer to the prefab's components. You know, the cloned game object would say my components are the ones on the prefab still. And so we have to make sure that when we instantiate, we also remap all of the references between objects to kind of point to their cloned versions as well, so that we have the entire graph copied through. And this is something, again, we use the serialization system for. And we also use it for generating type metadata, something we call type trees. These are really important, and I'll be covering them. They've got an entire slide later on. So let's look at the architecture of this then. All right, what does it actually look like when we want to serialize something? So we've got an object of some sort, friendly little cube. And we want to end up with nice data laid out in JSON, YAML, whatever format, but something where it's all been kind of put out neat and clean for us. But the problem is that the data is not in a particularly organized format to begin with, right? It's got strange alignment, it's in weird places in memory, it's got fields and subfields that are pointed elsewhere and all this stuff. So how are we going to get from bits of data scattered around the place to this nice, clean laid out thing? It's the responsibility of two major pieces. There's something on the object itself that we call the transfer function. And then the second component is something that we refer to as a serialization backend. Confusingly, we will also sometimes call it a transfer function. It is not a function called transfer, unfortunately, like the first one is. But serialization backend is what it is. So these two pieces together are going to take care of this. The transfer function is going to be responsible for kind of going through the pieces of data that we're interested in. And the serialization backend is then responsible for mapping those to individual kind of reading and writing operations on the backend. So we start with, say, the transfer function understands the first thing that should be serialized is something called data, and here's a pointer to it. Like it takes a reference to the piece of data, the memory address of it. And it passes those over to the serialization backend. The serialization backend then is able to just directly take the name and do whatever it needs to with the pointer. And this is really important. We don't copy the data from the object into the backend. We don't even assume that the backend is going to read or write, or even that it's going to do either one of those. We just pass through a pointer saying, this is a thing we care about serializing, and it's up to the backend to decide what it needs to do. If it's going to read data, then it's going to load something off disk and pump it into that pointer. If it's writing data, it's going to load from that pointer and pump it to disk. It's kind of up to the backend exactly what it wants to do. So having done the first one, then transfer function will move on to the second one. So we have more data, and here's the pointer to the next one. And again, we'll pass it over to the serialization backend, which can write it out as needed. Okay? So that's pretty simple so far. Let's look at a little bit more detail in the serialization backend itself. So suppose we have our JSON document or something like that with nothing written out yet. And let's just kind of examine exactly what happens in the serialization backend. So we're given the name and the pointer to the first piece of data to serialize, or deserialize, or whatever, but in this case, serialize. This goes to a function in the serialization backend called transfer, which, if you're keeping count, means there are now three things called transfer function in this, but never mind. So the transfer function that's the entry point to the serialization backend. Everything kind of goes into that. And that will feed through the name and kind of set up for writing the value. When it comes to writing the value, though, there's a whole bunch of different ways we can encode things. So the backend will have these kind of separate functions for transferring basic data like integers and floats and so on. It has something slightly more complex for transferring strings. It has much more complex things for transferring arrays or maps or other kind of collections. And we somehow need to go from a transfer function to the appropriate kind of back-end individual value writer. But we want to do that based on the type of the thing that we're transferring. And for this, we use something called serialized traits. Serialized traits is a templated class in C++. Now, if you're a C# developer, you've probably encountered generics by now. C++ has a similar concept in the form of templates, but templates are a little interesting because they're actually completely generated at compile time. And one of the crucial things you can do with templates that you can't do with generics, as far as I know, is you can actually override what the template is for a particular type. And this is a technique called template specialization. So we have this serialized traits template that is then specialized for individual types, saying for an int, this is what it should do. So we pull out one particular instantiation for int, and then the transfer function can start doing its thing. It reads the data in from the pointer, goes to transfer, feeds the serialized traits. Serialized traits then says, use transfer basic data for this. Transfer basic data writes it out to the output in that somewhat confusing boinging arrow around the place there. So that's one value written out in the appropriate format. So next, we would look at another one. So now we have more data. And this one is going to be a string. So once again, transfer is going to pull out a particular serialized traits instance after moving the name through. So it pulls out serialized traits for string, which again is specialized to handle things in this way. Transfer calls serialized traits, calls transfer string, writes the value out. Okay? So far, so simple. Here's a slightly more complex one then. We now have yet more data. And this one is actually not a string or an int, it's a struct in and of itself. It has subfields. And what we do for this one is we don't have a specialization of serialized traits for every single type in the code base. There's like a sort of a default version that's going to get instantiated if we haven't specialized it. And what that one does is it bounces it back out again. So the transfer function feeds the serialized traits, which bounces back out again to another transfer function for the struct. And the struct is then able to call transfer itself and start feeding in its field. So the struct then starts feeding in subfield, which is moved through as the name. And then we say, OK, well, subfield is an int. So we'll pull out serialized traits for the int. And boing, 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 boom. Yes. Good. OK. And then at that point, it's done. It returns from transfer. And then as serialized traits kind of says, OK, well, now the thing the subfunction I called to do transferring of the subfields is done, then it kind of closes up the struct as it comes back out again. So you can see that we can control kind of exactly how individual types in C++ are going to be written out through the serialized trait system. We can actually specialize the serialized traits not just for a particular data type, we can do it based on which backend it is as well. So we can say, for the binary backend, we want bools to just be written as 1 and 0, but for the JSON backend, we want it to be written as true or false, for example. So let's look at a little bit of the code. All right, fingers crossed. I've never done this before, so we'll see whether this is intelligible. So let's look at renderSettings.cpp. So this is the object that lives in your scene that stores lighting settings. Oh, sorry, good point. Let's do that. That's better. There we go. Right. So this is the object that lives in your scene and stores fog settings, ambient light settings, halos, lens flare type things, I think. There's a bunch of stuff. There's a bunch of stuff in that. So every object type in C++ in Unity has this transfer function, even if it does nothing. And it's pretty simple. It calls the base class transfer your data. It sets a version number, and we use this for tracking when we need to upgrade data. I'll talk a little bit more about that later. And then we just start transferring individual fields. So each one of these things is a member variable of the render settings class. And this transfer thing here, this is a macro that just hides a little bit of repetitive code. It's equivalent to that. Okay, so it just saves us kind of typing out the name twice and typing out transfer twice and so on. So what we're doing here is we're passing this variable, passing it by reference in C++, which is invisible. There's nothing saying ref m_fog color like there would be in C#, but that's what's happening here, and the name as well. So this is the first part of us kind of handing over that arrow and that string to the serialization backend. And so we go through and we do a bunch of stuff, more fields, more fields, more fields. We occasionally will say, something like it's serializing for game release. So if you're building data to actually go into the player, then we're going to do some extra serialization. We're going to include a generated ambient probe in this case that we want to be able to just look up quickly at runtime, but that at editor time we'll just compute it on the fly because trying to cache and manage cache invalidation around it is a pain. And then so a little bit more. What do we do? Yeah, if it's game release or we're performing unload dependency tracking, then we'll also include the generated skybox reflection. Just more stuff. And then at the end, there's this transfer deprecated thing that deals with loading and updating fields from older versions of your project. So if you open a Unity 2 project in Unity 2017.1, it's going to have render settings of version 1 or 2 or something like that. And so as we come through to transfer deprecated, we have all these bits of sort of saying, if it's version 1 or earlier, which it can't be, then at that point, we didn't have a separate kind of sky, ground, and equator ambient color as we do now. We just had a single ambient light color. So we'll transfer that ambient light color using the name ambient light. We'll put it just into the sky color slot, and then we'll set the other two to be the same so that it's just flat in all three. So we'll just replicate it into all three of them. So whenever we're kind of upgrading and changing the data formats of things, we'll bump the version number, and we can just write a little bit more code in here to deal with whatever migration is needed. Okay? By the way, this is something that we do want to bring to you in C# as well, and I can answer questions about that at the end. So that's kind of what it looks like for an object to kind of feed the values in. Now let's look a little bit at one of the backends. Let's take JSON write. So JSON write class is one of our serialization backends. It's one that I added in Unity 5.3. And this is what actually spits out JSON for stuff. Now, you can see here there's a whole bunch of these transfer basic data functions for different types. So for doubles, for floats, for char, for bool, etc. In most cases, doing pretty simple things. Transfer for bool is set bool, etc. And I think somewhere down here we go. Here's the actual transfer function on JSON write. So we're being passed in some kind of data. And this, this tref is because it's templated on the type of data. We've got the name, and we've got some flags that we can use to fine-tune exactly how it's serialized. So we set up kind of the current nodes, and then we call serialized traits. Oh, in this case, JSON serialized traits. We have a special set of them for JSON specifically that transfer the data. And then once we're done, we add it to the current object that we're working our way through. And then we're done, and that's it. And then we'll return back, and then the calling code in render settings will move on and transfer its next field, etc. So that's that. Pretty simple, huh? I'm not seeing a lot of nodding faces. That's OK. It's all right. We do this so you don't have to. OK. All right. So I've just shown you the JSON write backend. But what do we actually have? We've got streamed binary read and write. And we use these for high-performance reading and writing of particularly player data, We will also use it sometimes when we're loading binary files in the editor or when we're loading from asset bundles, on the condition that we know that the data is exactly the right layout that we're expecting. If we know it's the right layout, then we use the stream binary read, stream binary write to just load things in. Where possible, we're just copying stuff, direct transfer into memory. So we're not transferring X, Y, Z, and W of a quaternion individually. We're just saying 16 bytes, bang, etc. We also have safe binary read, and this is what we use if we don't know for sure that the data format is what we are expecting. Safe binary read can deal with situations where some of the data is missing, or there's some extra fields, or it's in a different order, or something like that. As we go to transfer each field, it seeks back and forth to find the right one. And if it's missing, then it just kind of says, like, this is a no-op then. That's fine. Don't worry about it. We have YAML read and YAML write. Fairly obviously, they're going to read and write YAML. We have JSON read and JSON write, as you've just seen. And then we've got a few more. Wait, oh, that's backwards. Oops. Yes, there we go. We have remap p-pointer transfer. And this is a serialization backend, but this is the thing that we use for remapping references between objects when you've instantiated something. So it's going to run through as a serialization backend. It's not going to write any data or read any data, at least not to a backend. But it's having these references passed in as things to serialize. It can then, at that point, say, oh, I'm not interested in ints or floats or bools or any basic data like that. If it's an object reference, I want to get the ID that's been passed in, and I want to somehow look that up to get like what I should replace it with. So we're able to kind of run that through. And it's quite powerful because we let that thing actually have the remap table be plugged in as another kind of callback function. So this is really something more like, give me a callback on object reference transfer function. We can use this to just walk the object graph from any given route. So we serialize the object. As we go through, we'll get pinged on every other object that it references. And we can just store those, or we'll do whatever. We can rewrite them, we can store them, we can erase them, we can do whatever. And then there's generate type tree transfer. And this is, it generates type trees. I'm proud of that one. So this one is just taking all the information that's coming in about the name, what type the field is, and so on, and generating data, like metadata, that we can store with the file. And the type tree is then used by safe binary read to understand what the actual layout of the data is that's there. So what are the things that we are kind of thinking about? What are the things that motivate a lot of this design for us? Because I'm sure there's plenty of people in the room who are going to ask me questions about why doesn't the serialization system support this? Why doesn't it support that at the end? A lot of the time, the answers come down to one of these things. So the first thing is performance. Not just load times, but when we're using this for instantiating things, for scanning object references, for GC, for undo and so on, like it becomes very important that we can serialize and deserialize things very, very, very quickly. And this is one of the things that I think I found when I was writing the JSON serialization support. Initially, I was just doing that because people were frustrated that there wasn't something built in and everybody was kind of using these different third-party solutions. But as I implemented it and profiled it, I found that it was maybe 40 times faster than a lot of the .NET solutions, just because we've built so much around performance here. The second thing is robustness. It is incredibly important to us that your data kind of be correct. Right? You can't work in any environment where we are not guaranteeing that what you're loading is what you saved. Right? So it's super important that it's correct. It's also super important that it's predictable and deterministic and things like that. When we're going to write out data to a YAML file and you've got it in version control, if the values in there are coming out in a random order every time, you're going to have endless merge conflicts and diffs that shouldn't be there and things like that. So we have to make sure that we're going to write things out in consistent ways, that kind of thing. And backwards compatibility, yes, that's the other thing. So I mentioned the version stuff there. The serialization system, because of the safe binary reading and type trees and so on, it is able to handle kind of when we just add things and remove things. But It's important to us to make sure that we can upgrade where you are to what we're trying to bring in as well. We don't always get it right. It's something that I would say we're not very good at testing right now. But it is a goal of ours to make sure that we can, that we can still take a project from Unity 1 or Unity 2 and open it now, and all the data will still be correct. I mean, maybe some of the behaviors have changed and things need to be rewritten a little bit, but by and large, all the data should still come in and it should all still work. So a little aside about type trees. So one of these things, they are metadata about the serialization layout. So they describe, given just a buffer of serialized bytes, they describe, bytes 0 through 4 are the x component of this vector that's called m position, or something like that. And then bytes 4 through 8 are the y component, et cetera, et cetera, et cetera. They're defined per type, not per object. The size of all of your files, if we did this per object, would go through the roof. And it's also necessary for speed reasons as well. We want to generate these things once and then cache them. And then the third thing is, they're then used to kind of provide data safety and versioning support. So, whenever you're sort of saying, I want this value from the serialized data, we can use the type tree to figure out exactly where in the data that comes from and pull the value and know exactly which type it is and all of that stuff. Either from C++ or from an API like serialized object, serialized property that I'll get to later in the talk. So that's C++ serialization. I'm about halfway through, so okay. Let's talk about managed a little bit, so it's a bit more relevant to you all. Now, there's a kind of a light side and dark side to how this all works, because I've shown you the C++ serialization system. The managed serialization is not a separate system particularly. It's a layer on top. Like, we don't have a completely separate set of code for reading and writing JSON and YAML and binary and all this stuff for C# types compared to C++ ones. So what we have to do is we have to have a layer that kind of adapts all of your C# code on top of this system of transfer functions and serialized traits and serialized backends and so on. So there's two ways that this gets implemented in Unity at the moment. There's the light side, which is mono and IL to CPP. And for that, we have this thing we call a serialization command list that we generate at runtime. And it's a little bit like a tiny program that runs on a little sort of serialization VM. We have a bunch of individual functions that will transfer an int and then transfer with this serialization function and that serialization function and so on. We've got all of these kind of things in there as like little pieces of code, and then we stitch them together at runtime just once per type based on the types of the fields in your C# object. Then there's the dark side, which is .NET serialization. So this is on Universal Windows Platform and Windows Phone. And for this, we use a tool called Serialization Weaver. And this is hard code that we're generating at build time. Now, I'm not going to talk very much about the .NET side of things because, to be honest, I don't know it very well. When you start dealing with it, you have to deal with like C++ CLI. You're dealing with kind of bridging between C++ and C# in the .NET world, multiple assemblies and all this stuff. By and large, a lot of the time, when we want to do something cool with serialization, .NET is why we can't have nice things. So the sooner you guys can all move to IL2CPP on Windows Store, the sooner we can drop .NET, and then all of the good things can happen. But we know it's not quite ready yet. We're working on things like managed debugging and so on for IL2CPP, get the experience good. But we do want, at some point, to get rid of .NET, because it's kind of constraining us around serialization. Or at least I do. I assume everybody else does as well. So let's look a little bit more about how Mono does stuff then. So the little program that it's made is this set of serialization commands. And what is a serialization command? It's a function pointer. In C# terms, that's basically a delegate. In C++ terms, it's a delegate without all the crap. Plus a little bit of static info, like the name of the field and the size of things and so on. So yeah, so the field name, flags for it, are pointed to the actual field structure in Mono's metadata. We've got a function pointer for how we'd serialize array elements as well. We've got the number of commands after this one that deal with like substructures and stuff like that. so that we can maybe then repeat that over and over for multiple elements of an array. And if you've got iSerialization callback receiver implemented on any of your types, then we'd also have like information about how to invoke those methods. So like the pointers to the backend information that Mono has for invoking those methods. So we end up just building kind of all this information for every field on all your types. And it doesn't really have any concept of who owns any of this data, right? It doesn't really understand which C# class owns a lot of this stuff. So there's no concept in the command stream of substructures or identity and referencing between things and so on. It's just this straight flat list of load this and put it here, load this, put it here, load this, put it here, load this, put it here. Right. So a simple case for a serialization command would be something like an int. Well, the simple case in general is what we call blittable types, where we can just take whatever's in memory in managed space and just copy it through to native space, or even directly share the memory in some cases. So the marshalling the data in that case, there isn't really any marshalling to do. It's already in the format we need it, and we can just hand it straight over to the transfer functions on the back end. They can go and write it out. In some cases, we might do a little bit of conversion. Strings in .NET are UTF-16. In Unity's backend, they're usually UTF-8, so we do some conversion of string types, for example. And then having marshaled it through, it's then call transfer on the backend. So that's all that these little functions do, is they just sit on top of the serialization backend and allow themselves to be plugged together, like dynamically constructing that render settings transfer function, kind of piecing it together at runtime. Slightly more complex case, so having like an array of custom structs. We would have generated one set of commands for the substruct, and then we would have had one command at the beginning that says, now we're going to do an array of the following 8 commands X many times, but look in the data to see how many times it actually is, kind of thing. So that's a more complex one. Building the command queue then. So we do this just once per type, or once per object type. So if you have a little struct that's used in a whole bunch of different mono behaviors, we do still end up kind of regenerating the commands separately for each mono behavior, even though you're kind of reusing the same struct. But for each field, what we do, first of all, we check that it kind of meets the rules for inclusion. So it's not private, it's not marked don't serialize, it's not static, it's not a special framework level field, things like that. Then we look up the actual kind of function pointer based on the type of the field. So we just have a big map of these things. We just have a big map of, for serializing an int, here's the one you want, here's the one you want for arrays, here's the one you want for fixed length arrays, and then here's the one for bool, and here's the one for uint32, and then et cetera, et cetera, et cetera, et cetera. So sometimes adding support for a new type to the serialization system is just a matter of adding those little extra adapters and then adding an entry to the list. I've done this recently for datetime, for example. Then we have to create the static info, which is all the information about the name of the field and the pointer and the size and the mono type token and all of these things. We just populate that thing. It's fine. And then once we've done that for every field, we cache the result as just a long chain of commands, like a program, a sort of serialization shader for that particular backend and that particular set of flags as well. Because we might, for example, use stream binary write to write this thing out in the editor and also to use it to write it out in-game. But the data that we'd write out in the two cases are separate. There are some fields present in one case that are not present in the other, so we don't want to kind of mix and match the command queues. Yeah. Right, add a little bit of C++ again. So, let's see. Let's start with transfer scripting object. So as you can see, there's quite a lot of comments. It's a good thing. It's needed in this case. So this is where we start with stuff. So we've been passed in some serialization backend, some scripting object we want to serialize, the type of the object, and this monoscript cache, which is where we store any cached serialization commands, amongst other things. So we start going through. We do some assertions. We calculate some kind of signature for the transfer function. And this is the thing I was saying about how the flags might be different. If the flags are different, the signature will be different. So we try and find the commands in the cache. And if we succeeded, if we didn't succeed, then we go and we build them. So build serialization command queue for these args, this command queue builder, et cetera, et cetera, et cetera. And then we have the commands. And then lastly, so we got the commands from the cache. If we couldn't get them, we built them. And then finally, we execute them here. And then we do a little bit of cleanup. If we step inside this one, what does it look like to execute this little program? Well, we've got the serialization command provider, which is just our array of commands that can just provide them kind of as a sort of iterator over that. So we set up a little bit of runtime information. This is the transfer function we're using. This is the object we're transferring. And we just say, while there's any commands left, grab one and execute it. So it's very, very simple. There's no branching or looping or anything like that. We just run the whole program start to finish. And executing one of these commands, well, as I said, a serialization command is a function pointer, which is that thing, and the static data. And all we do is we call the function pointer with the static data and a little bit of runtime info that is the specific object that we're dealing with right now. Okay? So it's very, very, very simple. And a very important point about all of the code I've been showing you here is that there's very little in the way of virtual tricks or indirect calls or things like that. We've got this function pointer stuff here. That's done very deliberately and very explicitly rather than using virtual functions. We want to make it very obvious to anybody who's reading the code that this is where some kind of slightly odd thing is going to happen. But all of the rest of the code, it's all templated, which means that we're generating completely separate implementations for all the different types. We do that so that the compiler can then inline it all again. So we've got things broken up into functions, templates, specializations, etc. A lot of the serialized traits maybe are going to be one line of code. But the compiler is able to take all of this and just smash it back together again and optimize the hell out of it, okay? Which it can't do when we are using virtual functions and things like that. So we end up trading code size for speed. It's faster, it's all inline, but it's bigger because we've got all these separate implementations of it for different things. There are some places where we've made changes to kind of bring the code size down that have been quite useful, and it's something we're going to keep looking at as kind of ways to improve this further. So that's kind of the trade-off that we make, is we increase the code size a bit in order to get kind of speed out of it. Right. So just to finish up. So last little section, and then we should have time for questions. So let's talk a little bit then about working with serialized data directly. So I mentioned before, we've got this type tree that allows us to understand some serialized blob of data, allows us to understand what's there, allows us to operate with it. And you will see us use the serialized object and serialized property classes to do that. So if you've ever written any editor extension code, you've probably used these types already. But these will let you directly operate on serialized data without us having to load or create any C# objects. This is the thing that's really powerful about it. You can take 10,000 heavy monobehaviors and open up a serialized object on them. We'll take the serialized data, but we won't spawn any actual C# classes for you, because it's far faster and it means much less garbage collection. So you're then able to kind of directly reach through serialized property. Serialized property is kind of a wrapper around parts of the type tree system. So it understands, it looks up in the type tree, but given the path that you're asking for, and then it understands the type tree says, oh no, this is an int or a float or an animation curve or whatever. So that's how that works. Okay. So that's what the type trees get used for. So. In conclusion, that's how Unity serialization system works. I wasn't really sure exactly what you guys would want me to cover, kind of beyond what I've done, so let's stop it there, and I will take some questions. So we've got about 15 minutes. There's a microphone in the middle here, if people would kindly, if we have questions, if they come to the mic. And I will try and answer anything you got about any part of serialization or anything.
Okay, so does this work? Okay, it
Yep.
does. For those of us who are writing like our own custom serialization systems built on top of the iSerialization callback receiver interface, often we need some more like context for like why is this particular like serialization call being invoked? Like for example, we optimize for build time data, but we have to detect this is happening for a build. So right now we have to do a stack trace in the editor and check are we coming from the build pipeline class, and you know it's horrible. So you have plans for providing more contextual information.
Right, so I suppose the obvious thing to do in that case would be to give you some way to get at the flags on the serialization backend that's being used, right? It's not something we expose today. I'm not sure off the top of my head how we would expose it without breaking all of everybody's code. And that's usually the problem with all of these things. But if we could find some way to let you ask, like, what's the flags right now? You know, are you serializing for game release? Are you doing, you know, are you trying to find assets that are being referenced for garbage collection purposes and things like that? I think it would make a lot of sense to expose that, yeah.
Thank you.
Hi. I have a question about the serialization of generics, because we have some problems when you have, for example, lists of lists. And I want to ask why, or what is the problem there?
So this is one of these situations where .NET stops us from having nice things. I think it's probably possible to solve, but it's one of these situations where we end up having to generate a ton of code for all these things that is intractable or not practical to do on .NET. Most of the generic stuff, yeah, because they don't actually instantiate all the generics at build time or something like that. And so we don't actually know what's there in order to generate serialization code for it in Serialization Weaver. I think that was the explanation that I was told. When we drop .NET someday, then yeah, it should become much more straightforward to actually implement support for generics properly. I don't know about list of lists immediately, but certainly being able to have like structs that are generic, that have some generically typed members. Because you have to deal, because I think in the mono embedding API, you get, there's a difference between like the non-inflated type, which is the completely generic version, and then the one that's been inflated with specific generic parameters, and there's a little bit of juggling we have to do to make sure we're working with the right one. But in principle, yeah, it should be entirely possible for us to just say, well, you've given us my struct of int, so anytime that you have a t, we'll just read it as int. Like, it should be possible. But we can do that at runtime with the mono stuff. It's, as far as I know, it's .NET where we start running into trouble.
Okay, thanks.
While you're getting there, I'll just say, so I mentioned that the version stuff and kind of dealing with older version code is something we want to expose. There is actually a slightly stale experimental build of that on the forums right now. If you look for something called script data upgrade, the intention is that we give you this system so that you can take it and you can, particularly if you're an asset store author or you're trying to, you've got a lot of instances of something in your project and you're like, actually, I want to change the way this is laid out. If you're renaming things, maybe it's easy today, but if you want to kind of, you've decided halfway through your project that trying to represent everything in feet and inches was a really bad idea, and you want to kind of convert everything to, meters, you could write one of these little upgrade objects to do that and kind of bump the versions on things as you go. So if you're interested, go and give it a try, give us feedback in the thread. It is still something that is ongoing, even though there's not been very much on it for a little while. So we're going to get back to it and going to get it out there. But yeah, okay.
Could you comment on problems serializing polymorphic types that are not based on Unity objects?
Right. So there are already situations where we can and do serialize structs or classes that are just plain old C# structs or classes, right? If you pass them to JSON utility, it can take a serializable struct of any without a specific clever base type, and just serialize it. So clearly it's possible. So the first problem is we have nowhere obvious to cache the result, right? I mean, JSON usually does not attempt to cache the command queues that it's generated for these things. It will do it for, if you serialize an entire mono behavior or scriptable object, then it will. But if you are just handing it a generic struct, sorry, not a generic struct, some arbitrary struct, it will generate the commands and run them and then throw them away. Now, could we just do that for everything? I mean, I guess the question is then, what does the API look like? How would you just expect like a sort of a serialized dot serialize this and you pass it some object, or?
Just to be, my question is more like about the case when we have a field, let's say class base. It's a field in a mono behavior, and where you have the data type that you assign to it is derived from that.
Oh, polymorphism.
Yeah.
Yes, that is another topic entirely. Basically, we do not store any information in the serialized data about what the C# types were, right? Well, the biggest problem with this is that the command queue would be different depending on the data. The type tree would be different depending on the data. So if I have a reference to base, and base has one field, and then I have derived that derives from base, and derived has 10 fields, then the command queues have to actually be different. But I don't discover that until I hit that field, right? So what we end up needing is some capability in the serializer to kind of get halfway through the program and then conditionally run some other command queue. And we don't have that today. Now, it's something that I think we should do. It's something that I want to do. I'm not going to say anything about like specific roadmap because I can't say anything about specific roadmap for it. But increasingly internally we're running into it as a problem. A lot of the stuff we're building, like the new input system, for example, those guys have had to do some pretty horrible things with JSON to kind of get around this stuff not being properly polymorphic. I think even when we do it, it will still be kind of opt-in. Like you'd have to mark specific fields as this one might not actually be what it looks like, guys. And so then we can kind of then go and check this stuff. But because we want to be very, very, very careful that we don't sacrifice performance all the rest of the time. But yeah, what it ends up coming down to is something like we'll have like a library of type trees available of all the different types that it could be. And then we'll store what the actual type was, and then we'll be able to kind of look up the type tree, generate more commands from it, and kind of run those on the fly. Something like that. But it's something that hopefully we'll be exploring next year. Again, I'm not saying anything about shipping. Exploring doesn't mean we find anything. But it's something that I want to spend some time on and try and figure out.
Okay, thank you.
Any more for any more?
So for serializing different formats, there's probably, for each format, there's like many different solutions and even mostly open source. I was thinking what was missing in these solutions that existed for years and been optimized for years that Unity saw that as something missing in that and had to do their own rewrite from scratch, probably.
So it's an interesting question. I mean, this is not from scratch. This is actually, this design is quite old. I think someone was telling me the other day, this design is very similar to the design in the old Microsoft Foundation classes, for example. I think when you look back, so firstly, bear in mind that the system dates back to when Unity was first created, right? We're talking about something that's been around for 10 plus years that affects every single class in the code base. Not just the object classes, but like little structs all over the place as well have this. If we were to go and try and change it at this point, it would be a pretty massive operation. And we would need to do so in such a way that does not break anyone's data in any project anywhere, right? So it's a pretty tall order. And so I wonder how many of the solutions that we'd look at today in C++ actually did exist back then. It's one of the things I'm not sure about. There were some things around that would do, for example, loading and saving data to disk. But as I've discussed, we do a lot more with that as well. A lot of the time, really, the serialization system is just a big visitor system. It's just a way to visit every piece of important data in an object, right? So, I mean, that pattern is very old. And the specific implementation, I mean, I don't know. Yeah, nobody tried it, I guess, is sometimes the answer. Yeah, you'd have to ask guys like Joachim, kind of, when you originally made the serialization system, why didn't you use X instead? And the answer might be because we didn't know what we were doing back then, because it sometimes is. But it might also be because we tried it and it was bad, or we tried it and it wouldn't work on mobile, or we tried it and it used way too much memory, or something. And there's a lot of serialization systems that are not built for game scenarios in particular. Like there's a lot that will do very complicated object graphs, but you don't want that. You want just like very, very fast buffers of data that can be loaded in very quickly and stuff like that.
Okay, thank you.
Anyone else? We've got about 5 minutes left.
Cheers. Regarding dictionaries, is there any sort of update on giving us a serializable dictionary so we don't have to keep writing them ourselves in every project?
Serialization of generics, yeah. Yeah, I think as I said before, it's basically we have to try and get rid of .NET.
It's more to the point like we write, at least at our studio, we write one ourselves. It's completely possible to do.
Right.
Maybe to give us like an actual collection itself, a serializable dictionary, or maybe with a flag.
Oh, sorry.
Different.
Sorry, you're asking just about serialization of
dictionaries, hash sets, that
right,
kind of
okay,
thing,
okay, sorry, I misheard you. Right, yeah, it's quite high on the JSON roadmap in particular, because there's a lot of people who want to be able to do, you know, unstructured data, or like, I don't know what my keys are, etc. There are some interesting problems around it. The first one is we cannot just kind of blit data from a dictionary, right? The internal structure of a dictionary has, you know, hashes and link tables and so on going on inside there. It's not really going to be practical for us to try and work with that from C++. So we have to do a managed call in, and then we'll do something like extracting all the values and all the keys into arrays and passing them back. That can get quite heavy because it means that we're doing a managed call and an allocation or pair of allocations for every dictionary that you want to serialize every time you serialize it. So that's one of the things that makes us go, ugh, maybe not. But there are ways of kind of restricting it to make it a little better. So for example, I think it would be easier for us to do dictionaries that only supported strings and ints and enums as key types, which I imagine would be enough for like 90% of people anyway.
And game objects.
Sorry?
And game object references.
Probably. It's a little more complex, that one, but probably. Yeah, or like some kind of object reference. So you'd be able to have a dictionary of texture to bool or whatever, I guess, as well. So there's the problem around kind of marshalling the data. There's the problem of stable serialization as well. Dictionaries aren't sorted. And that is a big problem then, because we want to make sure that when you're adding something to a dictionary, it doesn't reorder everything in the thing, so you get a massive diff in your VCS. So it has to be something where all the keys are sortable, for example, and we just have to actually enforce that. And then the third problem is UI. You know, if you're going to have a dictionary and we display that in Inspector, like what's the nicest way to do that? And I know that there are some packages on the asset store that have like explored different ways of doing this. I don't think we've yet had a chance to kind of sit down and like see whether any of them have like done it right as far as we're concerned. But making sure that we can handle, you know, what happens when you try entering a duplicate key. You know, should we let you reorder keys, or if we're going to impose this sorting, like is that going to suck? You know, all of that stuff. So it's doable, but it has this kind of series of problems, and we need to kind of see whether or not we can do it cleanly. And then there's .NET. As usual, .NET is why we can't have nice things, because there the marshalling is even worse. Like there the marshalling is basically, I think it's crossing like a remoting boundary or something like that. It's nasty. So yeah, it might be another one of these things where we say, well, are we going to try and solve this for .NET, or are we just going to wait a little bit until .NET is gone and then do it? We're going to have to kind of try and decide one way or the other. But yeah.
Awesome.
Okay.
Thank you.
All right. Okay, 1 minute left if anyone wants to grab the last question. No? See, I knew I should have made like little cereal boxes saying Unity serialization that I could just give to people to motivate them for questions, but never mind. All right, okay, well in that case, that's me. I've been Richard Fine. I'm Superpig on Twitter. Hit me up with questions if you come up with them after this talk. But otherwise, thank you very much.